Thank you very much for having me to the conference. My name is Dr. Chin and my co-author is Dr. Simon C. The title I'm going to present today is a max fusing gated recurrent units and ensemble classifier for intelligent acoustic classifications. As for introductions, an audio-based context recognition system could classify sound from different devices and scenes. As you can see, this is the different devices and this is from different scenes. Different devices means that the acoustics sound can be recorded using different mobile devices. As you can see that the color is different, and for different scenes it means that we can use the same mobile devices, but we can use them to record the different scenes. So today the data set that I'm going to use is from the DCASE2020 Task 1. This is the link that you can check for the details. Let's carry on with the introductions. The top performing system in the DCASE2020 challenge consists of multiple models using CAN. Instead of log mail spectrograms for feature extractions, wavelet time scattering has shown to perform well. The extracted features are insensitive to translations, rotations, and small deformations by the wavelet scatterings. And it also can transform and produce a more accurate classifier in dealing with variations in the ASC. Besides CN, gated recurrent units is one of the main gating mechanisms having memory cells that can work well with temporal informations, which is the time informations, and to solve the vanishing gradients problem in the RNN. And GRC has only 2 gates for updates and resets instead of 3 gates, which is used in the LST as shown here for classifications. And this paper we are using the GRU, and the GRU configurations can be seen here. The GRU layer sequence length can generate different classification accuracy and FY the F1 scores. So in this paper, a lower sequence length of 1900 is selected, and additionally the hidden unit of 950 and 250 is selected because it gives the highest classification accuracies around 84% and F1 score is around 83%. And we know that if we try to increase the hidden unit beyond 2 layers, which is currently we are using 2 layers, we will find that it does not improve the classification's performance. And this is the configurations of our GRU units. We have GRU unit 1 and drop layer, GRU unit 2, drop layer followed by the fully connected layers, softmax layer, and followed by the classifications layers. The proposed methodologies. So we have the audio signal in the waveform, and we first convert into the mono, which means 1 channel, and the scattering coefficients are averaged over the 10-second audio clips. So this is the sound file, and the input signal has 290 dimensions from the wavelet scatterings, and the input size is of course 290 sequence is required. And the parameter of wave transform are the filter bands using 1D modeled wavelets. Resolutions Q1 is 1 and Q2 is 4. And the duration of these wavelets as shown here is 0.75 seconds of the averaging filters, and is used for the modulation structures durations, and the sampling frequency is 44,100 Hz. And we have 2 filters. One filter has a resolution of 4 and the second filter band has a resolution of 1. So this is basically from this sound file, and we go through the wavelet scatterings. Alright, so this is the process I was trying to explain in this slide. And next, after the average data augmentations, which after you use a mix out basically, alright, so we combine a set of classifiers such as the LDA, RDA, and the QDA with the different predictors covariance treatments to produce better classifications performance than the single classifier. Alright, and then if we look at this, the output of each classifier are combined via the majority votings. Okay, to have the example model means that a few different models together, and this we name as an example random subspace discriminant classifier. And then next, if you look at the right hand side of this flowchart, the output of GRUs and the ensemble classifier are maximally fused to compute the sound coming from different device. So as I mentioned, we use a GRU and then there's a predictions, and we fuse it with the one that we've done previously to have a final predictions of the device, whether the sound come from different devices. And we also use the same process to classify the acoustic scenes, alright, and that will means that the second line that we mentioned, that we can classify the scenes just according to whether it come from the parks, station, metros, airport, and bus, and so on. So we have two results. One is the coming from the devices, one coming from the scenes. So for data sets, as from the scenes, you know that there's 10 cities. I mean, for the devices, it also recorded from 10 cities, and there's 9 devices. As you can see from there, A, B, C, 3 devices that is real, and the S1, S2, S3 to S6 is simulated. Okay, and just note that for training segments, we do not have S4 to S6 devices. But we have it for the test segments. Okay, and so it seems that it makes the evaluation more difficult as the data set is not seen during the training stage. So for data set, you see that in total there's 64 hours. Total segment is 33,040. Training segment is 13,965, and the test segment is 2,970. So for the result wise, we use our own laptops, this Intel Core 6 cores and GeForce RTX 2060 to run the experiments. For result ones, we compare the devices between the different example classifier, and we know that there's many classifiers, so we compare with the k nearest neighbor, big decision trees, and so on. So we find that the random subspace discriminant classifier perform the best in classifying the device, and it gives a 72.8% and the F1 score of 70.6%. So in general, the F1 score is more conservative as compared to the classification accuracies, and the amount of dispersion from the mean value of result is relatively small as compared to Kn. And you find that the Kn is this itself has a bit lower classification accuracies, which is 59.2%. Is basically quite sensitive to value of K of the nearest neighbors. And for this Adam boost and the best bad decision tree produce almost a comparative result, but it's still inferior to the proposed classifiers. And also the decision tree using the LB boost and total boost has a poor outcome due to the larger number of iterations, resulting in the slightly over complex composite classifier, resulting in the less accuracy results. And for the multi-class naive Bayes classifier does not perform due to the assumption that the features are independent, which in this case the feature is not independent, they are dependent from one another. So for result 2, we just look at the device, which is the classification results, and this is the confusion charge for our proposed ensemble subspace discriminant classifier. And you can see that the S4 and S6 is showing around 67.3 to 87.6%, and the true pass rate of S5 is 69.5% compared to S4 and S6 is quite low. In average, if you just average this out, you will find that the methods which is using the ensemble subspace discriminant classifier is around 72.8%. And for the result 3, which is basically the fusions of the GRU and the ensemble random subspace discriminant classifiers, and that's the fuse model, as you can see from the right hand side, and this 73.2% is higher than the individual, which is for this case 72.6 or 57.1. So this will give an average of 73.2%, which is 90.1% higher than the baseline results. So for the baseline result in the DCASE2020 competitions, this is what they have given us. This average between all the device-wise, their accuracies is 54.1%. And they are using the CAN, as you can see from here, which is the common structure, which has the CAN layer 1, 2, flattened, dense, and this is the output which use the softmax activation because of the classifications. So detail you can read from this paper here. So for result 4, we look at the scenes, not just the device. So we max fusion of GRU and the ensemble subspace discriminant classifier. As you can see from here, the right hand side is the result of the fusion between the GRU and the ensemble subspace discriminant classifier, and you can see that here we get a higher 77%, which is higher than just the individual by itself. And compared to the proposed max fusion model, the average scenes wise classifications accuracy of these both fusion is actually higher. And the max fusion of GRU and the ensemble random subspace discriminant classifier in the scenes wise classifications perform better than the device wise. So this is 77% as compared to previously 73.2%, which is the device wise. So the winner of the DCASE2020 challenge use is a Snapshot example deep learning neural networks. So it has an accuracy of 76.5% compared to proposed max fusion methods. Our device wise accuracy is a bit higher, okay, 77%, and it remains higher than the baseline 54.1%. So the computation time is actually shorter as compared to the Snapshot example deep learning neural network. As conclusions, the max fusion of the wavelet scattering ensemble classifier and the Gated Recurrent Units for audio devices or sources and scenes classification was proposed, and the framework uses wavelet low-pass scaling functions to generate a low-variant representation of the real value time series data. And you can see from the results after the mix up and the process and the flowchart that we propose, the scenes-wide classification performance is 77%, which is 3.8% higher than the device-wise classification that is 73.2%. Definitely is better than the baseline that is 19.1%. But for future work, we will try to use the more advanced feature extraction methods to increase the features data, and we also try to use the data augmentation methods such as the GRU, which is a generative adversarial networks in audio context recognitions. So with that, thank you very much.